Okay, so our last video for today's lesson, biologists wish to cross pairs of tobacco plants having genetic makeup of GG, indicating that each plant has one dominant gene and one recessive gene for color. Each offspring plant will receive one gene for color from each parent. The following table, often called a Punnett square, shows the possible combinations of genes received by the offspring. My biology students in the class will appreciate this. So we've got parent 1 and parent 2. These are the different possibilities for their offspring. Now it says the Punnett square suggests that the expected ratio of green, or GG, to capital G lowercase g to lowercase, should be 1 to 2 to 1. In other words, the biologists predict that 25% of the offspring will be the dominant, green. 50% will be yellow-green, and 25% will get both recessive genes, and they'll be albino. So these percentages that they've given you, 25, 50, 25, that's the claim. That's what they're claiming they would expect to see. All right, so that's going to help us calculate our expected counts. Now, we obviously want to look at some observed counts. So if you look below, it tells us what we see for observed. To test the hypothesis, the biologists made 84 randomly selected pairs of yellow-green parent plants. Of the 84, 23 were green, 50 were yellow-green, and 11 were albino. So these are my observed counts from my sample. It says, do these data differ significantly from what the biologists have predicted? So what we want to do now is calculate the expected counts. What would we expect to see? Well, remember that we took a sample of 84, and we expect to see the claim from the biologists, 25%, 50%, 25%. So for the dominant green, we would expect that if our sample size is 84, we would expect to see 25% be green. So if you multiply that out, it gives you 21. If we wanted to see the yellow-green plants, remember my sample size was 84, well, we would expect 50% of that. So that ends up being 42. And if our sample size is 84 for the albino plants, we would expect 25% of those to receive the recessive genes. So that's the expected 21. Now we observed 23, 50, and 11. Is it too far off from what we expected that we don't believe the claim? That's basically what we're testing in a goodness of fit. So it's good when, it's good when we check the observed and expected counts in the beginning, because we can then refer to it later on in the test. So again, I'm going to look at this last sentence. Do these data differ significantly from what the biologists have predicted? That's kind of what I'm hoping to show. So if I'm hoping to show that they're different, we have to assume that they're the same. We have to assume that it is indeed what the biologists have claimed. So the distribution, the null hypothesis says the distribution of plant types is equal to the biologist's prediction. That is, capital G's are 25, 1 capital 1 lowercase is 0.5, and 2 lowercase is 0.25. So it's a little bit different than the previous example. We're not assuming that they're uniformly. We are trying to see if it matches the claim of the biologists. So our alternative is that they're not the same. The distribution of plant types is not equal to the biologist's prediction. Or you could say at least one of the predictions is wrong, because of course if one of the predictions is wrong, the whole thing is wrong. Okay, so our plan step, we of course have to name it. We're using a Chi Square goodness of fit test. We are testing all of the categories, not just one. All right, and we have to start with our random condition. 84 randomly selected pairs of yellow-green parent plants. I took that right from here. We know that it's random, okay? So then, because I did an SRS, I have to check the 10% condition. 10% 84 is less than 10% of all yellow-green tobacco plants, and I'd say that's pretty safe. I'm sure there's a lot more out there than 840 tobacco plants. So then again, we don't check a we don't check a normal condition anymore. We check a large sample size condition. So what we need to show is that all expected counts are greater than or equal to 5. And since we actually did that at the beginning of the problem, remember we did that up here? These are our expected counts. Every single one of them is greater than 5. So we have met that condition. So in the test, because I showed it up there, I could just do this, see above. You just have to have it somewhere referred to on your paper to show that you did indeed check the expected counts. You can't just say it. You have to show that you've checked it. So because I have it listed above, that's good enough for my check. Okay. So then, of course, we get to the do portion. I am going to, again, draw my picture. And remember that it is a skewed distribution. This is my chi-squared distribution. We have to label the degrees of freedom. Well, in this case, how many categories do I have? Hopefully you're thinking 3. So 3 minus 1 gives me a degrees of freedom of 2. So that's the degrees of freedom we're going to use. Again, we have to find what's our chi-squared test statistic, and then we're going to find the p-value from there. So we got to know the chi-squared. Formula for chi-squared is equal to the sum of the observed minus the expected squared divided by the expected. So remember, we just used the numbers above from the chart. We can look back up here where we have the list of observed and expected. We're going to do 23 minus 21 squared divided by 21. 50 minus 42 squared divided by 42. 11 minus 21 squared divided by 21. And again, you can do this quickly in your calculator by typing observed into list 1, expected into list 2, and then in list 3, typing in the formula. Okay, so I'm going to quickly write it because you want to always show your work. 23 minus 21 squared divided by 21 plus an observed of 50 minus an expected of 42 plus observed of 11 minus a 21 of an expected squared divided by 21. Okay. Now I'm going to go ahead and skip the calculator part. You can watch the last video if you need to remember how to do this in the calculator. But those components are 0.19 plus 1.52 plus 4.76. Those are these 3 components. So that gives me a chi-squared total of 6.48 if I add those up. So that's your test statistic. So we want to know how likely is it to get a test statistic that's this large or larger. So from here, we go to our chi-squared CDF. That's going to give us the probability of, or the area of this distribution, I should say. So chi-squared CDF of the lower is 6.48. The upper is anything larger than that, which is 999. With the degrees of freedom, we said earlier, was 2. Okay, again, you can watch my last video if you need to see how to type that into your calculator. I'm going to go ahead and just really small write lower, upper degrees of freedom. Just make sure you're labeling those pieces so that you show the AP reader that you know what these pieces are representing. So when you type that into the calculator, you get 0.039. Remember that this is your p-value. Okay, so we have our test statistic, we have our p-value. We've got the 2 most important pieces of the do portion. Okay, and then lastly, we have the conclusion. All right, I'm going to drag that up so you guys can see it. Assuming the null hypothesis is true, that we've got these, this distribution. There is a 0.039 probability of obtaining a chi-squared value of 6.48 or greater purely by chance. Since my p-value is small, this provides strong evidence against the null hypothesis and is statistically significant at alpha equals 0.05 because 0.039 is less than 0.05. Therefore, we reject the null hypothesis and can conclude the data differs significantly from what the biologists have predicted. Okay, now remember, because we rejected, I'm going to come up with my follow-up analysis, which is right here. You're going to just tack this on to the end of your conclusion. Why did we reject? What portion of this made us reject? Well, in our case, this is the largest component, 4.76. So I say that the largest component of chi squared is 4.76 because the counts of the GG, lowercase, plants were less than expected. Remember, there were 11 observed, but we expected 21, so that's much less than what we expected. So in a goodness of fit, whenever you reject, this would be your full conclusion. You want this extra sentence in here that goes a little bit further. Okay, so there's your first new test, goodness of fit. I hope between last video and this one, this is making a little bit more sense. Feel free to go back to the Skittles example from yesterday and finish out the goodness of fit and see if we believe Skittles' claim or not. Okay, so hopefully these videos aren't too boring and that you guys are getting this okay. Feel free to text me on Remind, and I'd probably be happy to hear from you if you have any questions. Okay, we'll see you later. Have a good day. Bye-bye.